Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture and this module is on the performance metrics. So, what we are going to learn in this module is we are trying to identify and evaluate the performance metrics for a processor and also discuss the CPU performance equation. So, if you look at the computer engineering methodology, you have technology trends that happen, various improvements that happen with respect to technology, and this will give rise to newer architectures coming in. So, you try to evaluate the existing systems for bottlenecks, try to come up with new architectures, and this process continues. So, while evaluating the existing systems for bottlenecks, you will have to have certain metrics and certain benchmarks based on which you will evaluate these systems. So, you will have to talk about benchmarks, and once you have evaluated the system, then you will have to look at having newer and newer technologies coming in. So, in order to evaluate it, you will have to, when you come up with a new design, you will have to simulate the new designs and organizations, and you will have to run these simulations on new workloads, and then you will have to implement the new generation system, evaluate the and the process continues. So, you try to evaluate the existing systems for bottlenecks and then try to come up with new techniques. You will try to simulate the new designs and organizations, try to run it on the workloads that you are planning to use, and then the process continues. So, basically when you are evaluating a computer system, you will have to look at how to evaluate the computer system in terms of its performance. So, why basically do you have to look at performance? You have to basically be able to measure the performance, you should be able to report performance, you should be able to summarize the performance. Performance is necessary because that will help you make intelligent choices about the computer systems that you want to purchase. It will help you see through the marketing hype. There is so much of hype happening about computer systems. Unless you have some basics about the performance of computer systems, you will not be able to manage this and you will not be able to make a judicious choice while purchasing the systems. And studying performance measures is also key to understanding the underlying organizational motivation. Based on what factors did people try to bring in these modifications so that performance will be improved. So, you will be able to understand the motivational aspects based on which certain innovations were brought in the architecture. So, if you look at some performance questions here, you should be able to answer some questions like this. Why is some hardware better than others for different programs? What factors of system performance are hardware relative? For example, if you want to improve the performance of a system, do we actually need to go in for a new machine, or is it enough if you do an update of the operating system, get a new operating system? Does the hardware matter, or is it the software that matters? And how does the machine's instruction set affect the performance? So, performance is important both from the purchasing perspective and the designer's perspective also. So, when you are looking at the purchasing perspective, given a collection of machines, you will have to be able to decide which has the best performance, the least cost, and also the best cost per performance. From the design perspective, you are faced with various design options, and unless you know have some idea about the performance metrics, you will not be able to decide which will be the best performance improvement that you can think of, which will lead to least cost, and which will give you the best cost performance ratio. So, whether you are looking at a designer's perspective or a purchaser's perspective, both of them need to have some knowledge about the performance metrics, and both require these performance metrics for comparison, and they need to have these metrics for evaluation. Now, our goal is to understand what factors in the architecture contribute to the overall system performance and the relative importance and cost of these factors. So, if you have to define performance, performance means different things to different people. Say for example, take an analogy from the airline industry. if you have to choose between different types of aircrafts, what are the various factors that you will have to consider? Do you have to worry only about the cruising speed, that is how fast the aircraft flies, or do you have to worry about how far the aircraft can fly, that is the flight range, or do you have to look at how big the aircraft is and how many people can be transported at a point of time from one place to another place. So, these are different factors that need to be considered, and you can't expect a particular aircraft to satisfy all these requirements. So, you will have to decide which one is more important than the other factors. All three factors are important, no doubt about it, but all three of them may not be equally important. You may have importance for certain factors, more importance for certain factors compared to the other factors. So, the criteria of performance evaluation differs among the users and designers. The same holds good when you are looking at a computer industry also, because you have different classes of computer systems. Say you may have certain performance criteria which are important for certain types of applications, whereas they may not be so important for other types of applications. So, you should be able to decide which is important for which type of processor. All along you will have to be aware of the fact that you should never let an engineer get away with simply presenting the data. You always should insist that he or she should lead off with the conclusions to which the data led to. So, justify the reasons why you are getting these data. Only then you will be able to understand the internal architecture of the processor and make a judicious choice. Now, what is the role of performance? Hardware performance is key to the effectiveness of the entire system. So, performance has to be measured basically and compared. So, you should be able to evaluate various design and technological approaches, and different types of applications, different performance metrics may be appropriate. So, different aspects of a computer system may be most significant. Now, and the factors that affect performance may be the instructions that you use, the implementation of these instructions, the memory hierarchy, the way the I/O is handled. All this may contribute to your performance. The primary factor when you are looking at computer performance is time. So, when you look at time, all of us are worried about how fast a program executes on your processor. So, the most important performance factor is the time. So, when you are looking at a time, at the time being the most important factor, are you looking at response time or are you looking at something else? What do you mean by response time? Response time is the latency. You ask the processor to execute a particular task. How fast do you get the response from the processor? That is basically what is called the response time or latency. So, how long does it take for my job to run? How long does it take for my job to execute? How long must I wait after having given a database query? This is what is called a response time. Now, the other factor that might be important is throughput. Throughput, say for example, how many jobs can the machine run at a point of time? What is the average execution rate? How much work is getting done? So, the response time is the time between the start of the job and the completion of a job, which is very, very important to individual users. Whereas throughput is the total amount of work done in a given time, and this throughput becomes very important when you are looking at data center managers, when you are looking at servers, when you are looking at warehouse computers and so on. So, as I mentioned earlier, though there are different factors that you will have to worry about, each application may have importance, may give importance to certain factors. Response times may be important for certain types of applications, whereas when you look at servers and data center operators and all that, throughput becomes more important than the response time. So, you will need different parameter performance metrics as well as a different set of applications and benchmarks for embedded and desktop computers, which are two different classes of computers, which are more focused on response time compared to servers which are more focused on throughput. So, your benchmarks are going to basically differ depending on what classes of applications you are looking at. Now, to maximize performance, we obviously need to minimize our execution time. So, performance is inversely related to execution time. So, performance x is equal to 1 by execution time x. So, when I say x is n times faster than y, processor x is n times faster than y, then the performance ratios performance x by performance y is equal to execution time y by execution time x, which is equal to n. So, when I say the execution time of a processor is n times higher than the execution time of the other processor, the performance is the other way around. So, decreasing response times always improves throughput. Now, this is an example showing the relative performance equation. If a computer runs a program in 10 seconds and another computer B runs the same program in 20 seconds, how much faster is A than B? So, if you try to get the ratio of performance A and performance B, you just take the ratios of the execution times of B and A, which is equal to n, which is 20 by 10, which is equal to 2. So, we know that since A takes lesser time to execute a program, A is higher with respect to performance compared to B. In fact, A is 2 times faster than B. So, execution time is a very important metric when you need to compare computer systems. Now, when you look at execution time, that is the time the CPU spends working on the task. It does not include the time waiting for I/O or running other programs. So, you know the processor does not run only your program, it may be running other programs also. So, it may be running a program, and when there is an I/O transfer that is taking place, it may block this program and then it may switch over to a different program. So, we are not considering the time taken for doing the I/O operations and all that. We are only worried about the CPU execution time. That is the time that the CPU spends on a particular program. Now, how do you find out the CPU execution time for a program? So, if you have to define the CPU execution time for a program, you know that you can find out the total number of clock cycles that a program takes. Each program is made up of a number of instructions, where each instruction will take a number of clock cycles to execute. So, if you are able to find out the total number of clock cycles for a program, and if you know the clock cycle time for each of these clock cycles, then the CPU execution time can simply be calculated as the product of the total number of CPU clock cycles for a program and the clock cycle time. And because the clock cycle time and clock rate are inversely related, this can also be written as CPU clock cycles for a program divided by the clock rate. Now, because you know that the CPU execution time is a product of these two factors, you can improve performance by either reducing the length of the clock cycle time or by the number of clock cycles required for a program. And what is meant by a clock cycle, by the way? A clock cycle is the basic unit of time to execute one operation or a pipeline stage, etc. Now, the clock rate or the clock cycles per second, which is normally defined in megahertz or gigahertz, is the inverse of the clock cycle time. So, Cc, the clock cycle time, is equal to 1 by clock rate. The CPU clock rate basically depends on the specific CPU organization, whether it is pipelined or non-pipelined, as we will discuss as we proceed, and the hardware implementation technology, the VLSI technology that is used. Say for example, a machine clock cycle has been shown here. One clock period has been indicated. So, you have an off time, you have an on time, and both of that put together is one clock period. So, if you have a 10 nanosecond clock cycle, that relates to a 100 megahertz clock rate. If it is a 5 nanosecond clock cycle, it relates to 200 megahertz clock rate, so on and so forth. If you are looking at a 250 picosecond clock cycle, then that corresponds to a 4 gigahertz clock rate. So, the higher the clock frequency, the lower obviously is your clock cycle time. Here we have an example for the performance equation. Let us assume that a program runs on computer A with a 2 gigahertz clock in 10 seconds. Now, what clock rate must a computer B run at to run this program in a shorter duration, say 6 seconds. So, if you have to calculate this, because the CPU execution time is a product of your clock cycle time and the total number of clock cycles, if you want to achieve this in lesser time, in order to accomplish this, computer B will require 1.2 times as many clock cycles as computer A to run the program. So, if you do the calculations here, you find that the total number of CPU clock cycles that processor A requires is 10 seconds into 2 into 10 power 9, which works out to 20 into 10 power 9 cycles. Now, the CPU time for B, if you calculate using the same cycles multiplied by 1.2 is indicated here, and based on that, if you try to find out the clock rate, you find that the second processor should run at a clock rate of 4 gigahertz if you want to finish the earlier program a little earlier. Now, you have a problem here. When you have to find out the total execution time in terms of the total number of clock cycles multiplied by the clock cycle period, you have a problem of calculating the total number of clock cycles. That is because not all instructions take the same amount of time to execute. So, you will have to know the number of clock cycles that each instruction takes, and you should be able to add up all these clock cycles to find out the total number of clock cycles. Because all instructions do not take the same amount of time to execute, that is, one way to think about execution time is that it equals the number of instructions instructions executed multiplied by the average time per instruction. So, how do you find out the average time per instruction? Now, a computer machine or an ISA instruction is comprised of a number of elementary or micro operations which vary in number and complexity depending upon the instruction and the exact CPU organization. Say for example, a micro operation is an elementary hardware operation that can be performed during one CPU clock cycle. This may be a shift instruction, this may be an add instruction, so on and so forth. And this normally corresponds to one micro instruction in a microprogrammed CPU. Thus, a single machine instruction or a macro instruction, what you call, may take one or more CPU cycles to complete, and this is termed as the cycles per instruction. Now, the average or effective CPI of a program is the average CPI of all instructions executed in the program on a given CPU design. So, this is an example to show you how you use the performance equation. Now, computers A and B implement the same instruction set architecture. Computer A has a clock cycle time of 250 picoseconds and an effective CPI of 2.0 for some program, and computer B has a clock cycle time of 500 picoseconds and an effective CPI of 1.2 for the same program. Which computer is faster and by how much? If you need to calculate this, then you know that because each computer executes the same number of instructions, it implements the same instruction set architecture. So, you can just find out the CPU execution time A as I is the number of instructions that get executed into 2 into 250 picoseconds, which is 500 I picoseconds. Similarly, if you find out the CPU execution time for B, it is again I into 1.2 into 500 picoseconds, which gives you 600 into I picoseconds. So, you can clearly see, because the execution time A is less than the execution time of B, A is definitely faster by the ratio of the execution times. So, if you look at the performance A by performance B, it is going to be 600 by 500, which is going to be 1.2. Similarly, if you are writing it in terms of execution times, it is execution time B divided by execution time A. So, if you look at the effective or the average CPI, computing the overall effective CPI is done by looking at the different types of instructions and their individual cycle counts and then averaging it. Say for example, to find out the overall effective CPI, it can be done as sigma I is equal to 1 to n CPI I into ICI, where I is the number of 1 to n is the number of instruction classes that you have. CPI I is the CPI of that particular ith class, and ICI is the number of instructions you have in that particular class. ICI is the count of the number of instructions of class I executed. CPI is the average number of clock cycles per instruction for that instruction class. So, basically what we can try to do here is, instead of finding out the total number of clock cycles for each and every instruction, what we try to do is we split the instructions into different classes of instructions, and we find out what is the frequency of these instructions and what is the average CPI value, which is the average number of clock cycles per instruction for that class of instructions. Once you know these individual CPI values and the individual frequency count values, you can just do a summation of these individual products. That will give you the overall effective CPI. So, the overall effective CPI varies by instruction mix. When you have different instruction mixes, one particular class of instructions, suppose if it constitutes 50% of the program, then you might have a different CPI value. If the same class constitutes only 30% of the instructions, you may obviously have different CPI values, because the CPI values are not identical for each class of instructions. So, and this average effective CPI is a measure of the dynamic frequency of instructions across one or many programs. This is an example that has been given here. Let us assume that you have 4 classes of instructions. You have the ALU type of instructions, you have the load type of instructions, the load type of instructions, and the branch instructions. And we assume that ALU instructions constitute 50% of the instruction mix in your program, load instructions 20% of the instruction mix, store 10% and branches 20%. And the next column gives you the cycles that each of these classes of instructions take. ALU takes 1 cycle, load instructions take 5 clock cycles, and store instructions take 3, and branch instruction takes 2. So, based on these values, you can always find out the CPI values. So, once you find out the CPI values, it is just a product of the frequency and the cycles. So, it is 0.5 into 1, 0.2 into 5, so on and so forth, and the sum of all this gives you the effective CPI. So, you can always find out the individual CPI values, and based on the instruction mix, you can find out the effective CPI values. Now, you have another example here where we are trying to find out how much faster the machine would be if a better data cache reduced the average load time to 2 cycles. So, initially you find that the load takes 5 cycles, and now because you have brought in an improvement in the system, the load time is reduced to 2 cycles. And you know that loads constitute 20% of your instruction mix. So, if you try to find out 20% of your instruction mix and 2 cycles, that constitutes about 0.4. So, the total CPI was originally, total CPI value was 2.2 originally. Now, it has reduced to 1.6. So, the relative performance improvement that you have is 2.2 divided by 1.6, which is 1.38. Now, how does this compare with reducing the branch instruction to 1 cycle? So, suppose if you look at branch instructions, that forms 20% of your workload, and it takes 1 cycle each. You have reduced it to 1 cycle now. So, the relative time is 0.2 here. So, the total CPI now reduces from 2.2 to 2.0, and the relative performance is 1.1. So, as you bring in enhancements to each of these units, you find that the CPI value reduces because the number of clock cycles that each of these classes of instructions take reduces, and once the effective CPI reduces, you definitely will have an improvement in performance. So, now having looked at all this, we will come to the most important equation, which is called the performance equation. So, we have already defined the execution time as the product of the total number of clock cycles into the clock cycle time, and then instead of defining the total number of clock cycles, we said the total number of clock cycles can be written as instruction count into the CPI value. Instruction count gives you the total number of instructions, that multiplied by the average number of clock cycles for every instruction, that will give you the total number of clock cycles. So, our basic performance equation can now be defined as CPU time is equal to instruction count into CPI into clock cycle, or instruction count into CPI divided by the clock rate. This is the fundamental performance equation, and this is a very, very important equation. So, if you have to improve the performance of a computer system, or in turn reduce the execution time of a computer system, reducing any of these factors will reduce the execution time and hence give rise to an improvement in performance. So, the CPU performance equation can be written as, so you are looking at the CPU execution time per program, that is nothing but instructions per program, which gives you the instruction count, clock cycles per instruction, which gives you the CPI value, and seconds per clock cycle, which gives you the clock cycle time. And execution time, you know, is 1 by performance, where execution time is instruction count into CPI into clock cycle time. Now, these equations separate the 3 key factors that affect performance. Now, you can measure the CPU execution time by running the program, because unless you measure these parameters, you would not know how to reduce these values. So, if you have to measure these 3 parameters, the CPU execution time can be just measured by running the program and measuring the clock cycle time. The clock rate is normally given for any processor, and to measure the overall instruction count, you need to use special profilers or simulators without knowing all of the implementation details. And CPI varies by instruction type and ISA implementation, for which we must know the implementation details. So, if you look at the aspects of the CPU execution time, so you have 3 factors which affect the CPU execution time, basically the clock cycle time, the average number of clock cycles per instruction, which is your CPI value, and the instruction count. Now, what are the factors that will affect each of these parameters? So, if you look at your instruction count, first of all, instruction count is affected by different factors. It depends on the way the program is written. If you are a skilled programmer, you use a crisp algorithm, you code it appropriately, then it is going to use less number of machine instructions. The first thing depends upon the algorithm that you are going to use and the skill of the programmer who writes this coding. The second thing is, once you have written a code, the compiler is responsible for translating these instructions into your machine instructions. Now, the compiler should be an optimizing compiler, so that it translates this code into fewer number of machine instructions. So, the compiler also has a role to play in reducing the instruction count. But again, the compiler can only use the instructions that are supported in your instruction set architecture. So, the instruction set architecture also plays a role in reducing the instruction count. The previous session we have looked at how the same operation can be implemented as different sequences of instructions depending upon the ISA. So, with the help of the ISA, the compiler will be able to generate a code which uses less number of machine instructions. The second factor is your clock cycle time, which depends upon the CPU organization and also depends upon the technology that is used. And the third factor is your CPI, which is the average number of clock cycles per instruction. This again depends upon the program used, because you may use complicated instructions which have a number of elementary operations. So, your average CPI value might increase. Similarly, the compiler may translate it using complicated instructions instead of using simpler instructions. So, the compiler may also have a role to play, and because the compiler is only using the instructions in your ISA, the ISA definitely has a role to play. And finally, the CPU organization has also a role to play in designing the CPI values. So, these are the various parameters that will affect these 3 factors, and by taking into account these factors and appropriately designing them, you will be able to reduce the CPU execution time. So, to summarize, we looked at how to define the performance of a processor and why this performance is necessary for a computer system. We have pointed out different performance metrics. We have looked at the CPU performance equation, and we have looked at the factors that affect the CPU performance equation, and we have also come up with different examples which illustrate the calculation of your CPU execution time using the CPU performance equation. Thank you.